Hello students, so in this lecture we are going to discuss about phase equilibrium. Now equilibrium is another essential concept that is best described in terms of thermodynamic quantity called Fermi energy, called free energy, sorry. And free energy is a function of the internal energy of the system and also the randomness or disorder of the system. So this can be called, it is a function of internal energy and disorder or randomness, and that is nothing but the entropy of the system. Now a system is at equilibrium if its free energy is at a minimum under some specified combination. You can see a system is equilibrium if free energy is at minimum and a specified combination of temperature, pressure and composition. In macroscopic sense, this means that the characteristics of the system do not change with time but persist indefinitely. That the system is stable. Let me see that. System is stable. Now, if there is a change in temperature, pressure, or a composition for a system in equilibrium, this will result in an increase in the free energy. You can see that. There is a change in temperature, pressure, or composition. For a system in equilibrium, this will result into a change in free energy. And in a possible spontaneous change to another state where the free energy is lowered. So change will be such that when it goes from one state to another state, the free energy gets lowered. Now the term phase equilibrium, often used in context of discussion, refers to equilibrium, and it applies to systems where more than one phase exists. So now phase equilibrium is reflected by a constancy with time in the phases characteristics of the system. So when you say phase equilibrium, we are talking about more than two phases, and we are talking about this is constant with respect to time. And in many metallurgical and materials system of interest, phase equilibrium involves solid phases. In this regard, the state of the system is reflected in the characteristics of the macrostructure, which essentially include not only the phases present but and their compositions. So, microstructure is very important. So, which is again is related to not only the phases but also the composition. And also the relative phase amounts. And the spatial arrangement or distribution. So these following things should be considered when we are dealing with a solid phase, and we are trying to establish or trying to understand the phase equilibrium between the different solid phases. Now, free energy consideration and diagrams, they provide information about these phase equilibrium, and it is necessary for the attainment of a new equilibrium. Now let's start with an example. We'll start with eutectic alloys. But the term eutectic means a solid is getting transformed into two different solids, solid plus another solid. So all the phases in the transformation are solids. Now, depending upon the composition, different type of microstructures are possible in the slow cooling of alloys belonging to binary eutectic system. So we'll be starting with slow cooling. Now so if we draw the phase diagram, we put temperature with respect to composition. The composition means we will be using lead. So this is the composition of the lead, and let's say the composition. So the diagram will look something like this. We have this composition is called C1, and this is the liquid here, and this line is called the Liquidus line, because above this line all the phases are in the liquid state. This is called the solidus line. So for the phase present here is alpha, So this is the liquid state. Here will be alpha plus liquid, and this is a state where there is a formation of another phase beta. So at this, if we look into the macrostructure at this point, just in the liquid, just along the liquidus lines, we'll see that basically you have the liquid phase L, and there are some solid phases of alpha being formed in this state. Whereas we considered the macrostructure air, so it will be mainly alpha phases and beta phases being formed here. If you look into this macrostructure at this state, so the composition turns like it's 10% of weight percent of lead here, and at this point it is 80 weight percent of lead here. So this is how the eudectic diagram, phase diagram looks like. Now the alpha phase, which is a lead rich alloy, this alpha, which is a so lead rich containing 0 to 2 weight percent of tin. Basically we are having this combination of lead and tin alloy. So this consists of higher percentage of lead, and while the beta phase, so this is actually concentration of weight percentage of tin phase here. So beta phase on the other hand contains 99% of pure